Hello everyone, this is the Introduction to TypeScript course. I'm Giuseppe Maggiore and today we're going to talk about object-oriented programming. Object-oriented programming is a major topic in computing. And even though TypeScript started out from JavaScript, so it mostly put its roots in a procedural style of programming, which later on became more and more functional. Well, still, TypeScript being a real-world language, it means that it has to support a lot more than just a single paradigm in a single-minded fashion. And, well, given that object-oriented programming is extremely useful, very widely employed by so many developers all over the world, well, it has been inserted and supported, and nowadays TypeScript can boast, I would say, a top-notch object-oriented structure. Object-oriented programming is based on this idea that we take a program, like let's say we have a program and we have some variables, we have a x, we have y, we have whatever variable we want, and then we have a series of functions like print x and y, which just puts them on the screen. Now let's finish printing them. Yes, x, comma, y, oops, dollar, and so on. And maybe we have other methods, we have other things, and at some point you might realize, no, I want to take these two variables together. So let's say we have a point, and in the point we have x is a number, y is a number, and well, then you want to generalize this a little bit, so you say, okay, prints a point, having some trouble typing today, print point, okay, now x and y come from P, very good, and maybe we also want to have other functions, for example, something that adds 2 points together. So we have P1 being a point, and P2 being a point, and we want to do something with them. Maybe, well, I don't know, we return a new point. Let's tell the function that it's supposed to return a point, and then we get some nice type checking. The x will be p1.x, and the y will be p1.y, obviously plus p2.y, and p1.x. There you go. Okay, so if we take a program like this, now let's define a couple of points. Let's say we have actually, yeah, let's just define an array of points. Yes. So points will be an array of points. I promise this is going somewhere. And then we start. X is 1, y is 1. X is 2, y is 2. And in a shocking hit of fantasy, x is 3, y is 3. And to top it off, x is 4, y is 4. Now we have an array of points, okay, and we can do things with them. So you can say, okay, for each point, just print it. But wait a second. So we map with print point, and for each we console.log. Very good. Let's run this little program. There you go. It looks like it's printing. Is it printing? Oh, how silly. No, let's say that print point. Yeah, let's turn this into. Oh, let's do this more prettily. No, I just want to rename it. Point to string. Yes, much more elegant. Yes, very good. Okay, so map with point to string is going to turn each point into the corresponding string, and then each of those strings will be printed on the console. Yes, much cleaner setup. Let's also put brackets around the points, then they will actually look a little better. Whoop. And I'm wondering now why is it looking so ugly. So let's make it a little bit more explicit. We want to just print the point itself. Let's not rely on whichever arguments console.log is picking from for each, because for each passes some arguments that you may ignore in the callback, and log is actually picking up on those arguments, like the index of the element and the context, which is the whole array. So let's keep it clean. Yes, this is much better. Okay, there we go. Now this little program works. Okay, so this program on its own would work, but let's say that at some point we also wish to add some more units of computation to this program. We want to add something that has to do with the web, with interface, with databases, etc. The problem of grouping things together does become a very serious problem, because at some point, if everything ends up in the same file, or even in a loosely grouped collection of files, well, things are going to be quite messy and unmanageable, and eventually we will not be able to maintain our code. And especially if dealing with a team of people, well, things become very chaotic very quickly. There is a solution, which are modules, where we basically state that we have a module, point, or points, or whatever, or I don't know, math dot algebra dot should whatever, not should oh, math exists already, obviously, apologies. Okay, yeah, we could say at least these utility functions, they all exist in inside the module. We can export the symbols we want to make available to other modules, and well, we would need then to import these symbols, etc. So it's all fixable. It all makes sense, but there is perhaps a better solution. Oh, and by the way, the module would be moved to another file, and then we have a whole import system, and that's doable. But object orientation offers us a more, you could even say, standard and accessible solution, which is to group fields like x and y inside the point and operations on those fields together into units of computation. And by combining data and logic into single entities, which we model with special constructs in the language, classes when we have both the data and the logic, an interface when we only want to model the logic, this is called object orientation. And a unit of data and functionality and logic is called a class. Let's turn this thing into a class. Okay, so we start with class point. The fields are defined exactly the same way. Then, oh, I broke it. Then we move the functions here up inside the point. Okay, now plenty of things are broken, so let's fix them one by one. Okay, let's start with the first complaint, because classes do require a little bit of adjustment. The first complaint is that x and y are not being initialized and are not definitely assigned in the constructor. What is the constructor? Well, how do we create an instance of a point? How do we initialize this little unit of code? We do so with a constructor. How do you create a constructor? Well, guess what? With the constructor method. Now, the constructor method may take parameters. It's actually quite advisable to take parameters that initialize the fields that have a sort of almost public external visibility. Inside a point, in every method of the point, in every function that contains logic of the point, including the constructor, we have a special variable called this. The name is an old name. It stems from decades ago. It's one of those things that some computer science scientists somewhere in a university decided, okay, let's call it this because it refers to this current instance or whatever. And 60 years later, we're still calling it this, and no one really knows why. One language bravely attempted to change the name this into self, that's Python, but it really feels weird at some point because then you have this little black sheep and it's doing exactly the same thing but really wanting to call it differently and hoping it will make a difference. So this it is. And what does this contain? This contains a reference to the area of memory where the currently, in this case, constructed instance of the point is stored. And what's in there? Well, the fields, the variables, the internal variables that contain the data for this instance. And I can say this.x is equal to x. X would be the formal parameter of the constructor, and this.x would be the field inside the current instance. And I just initialize x and y. Notice that the errors around x and y have disappeared. Okay, now, when dealing with turning a point into a string, well, there's actually a function for this, which is called to string. Okay, and we don't need the point as a matter of fact. Why? Because there's this. We could have been lazy. We could have said const p is equal to this. Not forbidden, but a bit unusual. Certainly makes the refactoring more comfortable, and there we go. Okay, how do we use this? We can now define an array of points. And we can create these points by invoking the constructor with new. I suspect that here the usual structural nature of the compiler is working, is doing its magic. And so I might be able, I'm really wondering whether or not this is going to work. Okay, this, no, something something is misbehaving indeed. I don't know why TypeScript is accepting this notation. I don't think it should, to be honest. I think that we might have stumbled upon a place where the TypeScript compiler is being too lenient. Because the proper way to initialize a new instance of a point would be this. We say new, the name of the class, and then between brackets the parameters of one of the constructors, because yes, we may have multiple constructors. Let me show you what this would look like. So we could have a constructor that initializes both fields with the same value. No, they don't seem to be allowed. Oh. Well, this is quite common in most languages, but apparently not in TypeScript. Okay, so usually TypeScript is overly complete with respect to other languages like Java and C#. In most languages, it's possible to have multiple constructors. Anyway, so 1 and 1, 2 and 2, 3 and 3, 4 and 4. Something that's actually nice is that it's somewhat easier to type the invocation of a constructor, because the brackets, the values, and the commas, the values are assigned to the fields based on their position. So when the position of the fields is clear enough, and anyway the IntelliSense will at least suggest which field you're assigning while you're typing, because then you can see, hey, the first one is X and the second one is Y. There you have to type less curly brackets and then name of the field, the colon, value of the field, the comma, etc. So this actually saves a little bit of typing, especially when there are more than 2, 3, or 4 arguments. Okay, let's see if this little program works. Yes, now it's working as intended, because these are instances of point, and so we can actually call to string and things work as they are supposed to. Okay. And, well, while on the surface this might feel a bit different from a procedural or a functional model of programming where data is stored in variables and passed around as parameters, and logic is built as a series of functions, etc. I would like to ask you to rest assured that all of these paradigms of programming, they mix very, very well. And some techniques for mixing are so good that they really are taking over the world. A few years ago, there were still debates about which paradigm would be the, let's say, absolute paradigm. Is object-oriented better than functional? And nowadays, the world has kind of secretly come to the peaceful conclusion, just you can use them all together, It's fine, it works. And yeah, I have to say, it's been beautiful to witness. All right, let's add one function. Let's call it a scale, which takes as input a factor and just scales the point. So we say that this.x is multiplied by this factor, and same happens to y. Okay, now what can we do? Now we can take one of our points and we can scale it. So points of 0 dot scale and scale it by 3. So what's going to happen when we print this? 1 1 will become 3 3. Okay, not very surprising. Because an instance of a point has its own little area of memory which stores its own x and y separately, we can invoke a method like scale which will act only on a given pair of x and y together, change them in memory, and yeah, just take it over from there. And all these little units of memory are independent little programs, or they sort of behave like independent little programs. Now though, I would like to discuss something that is insanely important and very, very often overlooked by especially by beginning practitioners, but also by more seasoned professionals, and this can be a very nasty source of very annoying bugs. What does memory look like in this bit of code? Well, we have the points, and the points, it's not just an array, it's actually a reference. Let's say it's the first reference. No, it's a reference. And let's call it reference 0. What does it mean? It means that somewhere we have an area of memory called the heap, which will contain a series of big objects that are stored as references for easier sharing of references. So now we have ref0, and ref0 is this array. And what does ref0 contain? Well, it contains references to all these points. So ref0 will contain ref1, ref2, ref3, and ref4. Because there are no variables that point to the different points that we created inside the array. Ref1, what will it be? Ref1 is a point. So let's simply say that this is point 1 1. Let's simply state how it was constructed. Then ref2 will be point 2 2. Ref3 will be point 3 3. And finally ref4 will be point 4 4. Okay, so this is how what memory looks like. Actually, because we have the stack, to be a little bit more precise, we could say that on top of the stack, we only have the points variable, which is ref0, and the heap is shared across all instances of the stack. So if we call another function, then we get with parameters a, b, and c, then we will find them here on top of the stack, and then on the lower level of the stack, in the global scope, we have the points. Okay. Why am I saying all this? Look what happens if I decide to say that points 2 is equal to points 1, 2.0. Okay, what does equal mean in this case? No, this is like the worst example possible. Points 1 is equal to points 0. Let's print this program. Let's run this program again. And you can see that, okay, the first one, which was 1, 1, has been scaled, so now that's 3, 3. But for some weird reason, also points of 1 has changed. And this was supposed to be points, this was supposed to stay, to keep the value 1, 1, because what we assigned to points 1, you might imagine, is the value of the point that contained x equals 1 and y equals 1. Let's actually print right before the scale. Look, here, perhaps a good idea to add console.log and then a bit of space between the two. Okay, so first we copied this value, which contains 1, 1, into the second element of the array. So they're both 1, 1, but that's because we just made a copy. But now, apparently, by changing the first one, the second also changes. And let's see what happens if we change the second one. We get the same result. Okay, this is very weird, because now, apparently, there's a sort of strange, unexpected warp gate or warp tunnel that connects the first two elements of the array. And this is not good. Like, our brains aren't even that good at reasoning in terms of warp tunnels. Like, it's not our normal experience in physical reality, and as such, it's not our expectation when dealing with code. Because classes are copied by reference, so we don't copy the content, we just copy the reference, meaning that after this instruction, memory is going to look like this. So the stack still contains the points, which is still ref 0, but points of 1, which is this one, has been copied to the value of points of 0, meaning that the array simply has reference 1 twice. The garbage collector is the tool that says, okay, it starts with the stack, okay, points, that's live, we have a reference to this location in memory, this is alive, then this also keeps alive ref1, ref1, ref3, ref4, no one keeps ref2 alive, the garbage collector reclaims it to free up memory automatically. This is like very embarrassing, because now when we call scale, now we call scale on ref1. So whether we write points of 0 or points of 1 dot scale, that's exactly the same, because they are both ref1. So what's going to happen is that, well, at this point, let me show what happens after. And the debugger would show this to an extent. Now ref1 is the one that's been changed. This is turned to 3, 3, and that's the reason why it looks like in the array the first two elements are different, but they both changed at the same time. But in reality, no, this array has the same element referenced twice. And all of these actual objects are called the instances, and every variable that is assigned to an instance is not really assigned to an instance, is assigned to a reference of an instance. Very, very, very important when dealing with with objects, to realize that we have these instances, and these instances are copied around and passed around by references. And this is different than the numbers or booleans or primitive types, because if you have an array of numbers, well, they are different instances, and if you try to copy them around, what gets copied is the actual value. So this kind of weird quantum tunnel behavior can only be seen when dealing with classes, well, and objects and other complex data types. So the objects that we define with curly brackets would also have this behavior. One pattern that is very strongly advisable when dealing with object orientation, especially for these container classes like point, is to make everything immutable, meaning that we mark the fields as immutable, as read-only. They cannot change, they can only be assigned once. Constructor doesn't change, but scale, well, we can't really assign x and y because they are read-only. What's important about read-only? Well, that when you call a method like scale, it cannot change the fields. And you might wonder, yeah, okay, duh, so what? So what? We make it immutable, meaning that we return a new instance of the point, which will contain the mutated value. Stay with me for a second. So instead of reassigning the fields, I return the new value. Now, a scale here doesn't really do much, but look what happens. Now we can very clearly state that, okay, I want points1.scale, which is now floating, it's not changing points1, so points1 is staying the same. So while I'm running points1.scale of 3, that's not really changing anything. It's creating a new value. Then I have to decide, okay, where do I put it? So now we're splitting the logic that mutates and as in creates something new that is based on something we had already, that is floating and creating a new point that is in temporary memory, and then we decide where do we put it. So now this program behaves much better, because now you can see that we're, okay, even though points 0 and points 1 have been copied to the same reference, well, because scale doesn't mutate blindly whatever it's called on, then we have control over where do we put the result of this mutation, obtaining a behavior which is a lot cleaner. And if you wanted to have something like like adding a point to another, now this is what it would typically look like. This is implicitly the point we've called we've called the method add-on. And now we just need the other, and what do we return? Well, we return a new point, so this is also quite immutable, where the x is this.x plus other.x, and the y is this.y plus other.y. And now what we could do is we could say that points of 2 is equal to points of 0, plus points of 1. Because this returns a point, now we can chain, we can say plus points of 2, plus, I could have also called it plus indeed, maybe it would have been more readable, maybe not, who cares. And now points of 2 will be, well, the sum of all the other points. And this kind of operands, well, this kind of chaining of operations scales really well. We can call any other methods. We could have add. We could have subtract. We can put the operations also with all sorts of nesting as we might want. So immutability also has this advantage that because every method returns an instance, on top of that instance you can immediately chain other operations. I like this. I find it very elegant. Classes, as we've seen so far, contain both the shape of this new data type we want to define. For example, if we had defined a data type point, we would have said, okay, the point has the x, the y, and then also methods scale, add, and toString. But the type wouldn't contain the body of the methods. Classes, on the other hand, contain the fields and also the method signatures, and associated with each method signature is the full implementation of the body of that method. Okay, sometimes though it's useful to take a step back, or perhaps an intermediate step, and just define the required shape in terms of the expected methods that a class is supposed to have. This kind of definition, which only exists indeed in the domain of types, is called an interface. This is very useful when an interface can then be implemented in multiple ways, but the code consuming and using the interface does not care. Okay, let's jump right away into an example. Let's delete this one. Okay, so let's say that we want to define a bitmap. A bitmap, which apparently I cannot write. Okay, a bitmap is an image, and an image is basically just a matrix of pixels. Let's define a pixel as R, now you know what, I'll be even lazier, R, G, and B. So the red, green, and blue components. Okay. Bitmap has a setPixel method, which takes as input the row, the column, the pixel, and simply stores it into the bitmap. Now, what does it mean to store it into the bitmap? We don't know. And frankly, at this point, we don't care. It might be that we save it on the screen, might be like a texture in a video game that they are represented with bitmaps in the GPU memory. It could be just an array of arrays of pixels. It might be that we save it on a hard disk, on a file, we send it to an API. It doesn't really matter. The bitmap, as is, represents just what do we expect to have when dealing with an image. And we expect to be able to set pixels and, you know, just for completeness, also to read the value of a pixel at a given position. Okay. Now, in a good implementation, obviously, there would need to be more. There would also need to be the width, the height, etc. But for now, we don't care. Now we're also going to define another interface. This is where things become interesting. Let's say we have shapes that we want to be able to draw on bitmaps. And, well, what can a shape do? It can draw itself on a bitmap that is provided as input. The thing that's very interesting about this piece of code is that the bitmap interface doesn't really say anything about how the bitmap will be implemented. And I've already sketched a few interesting implementations. We're only going to build the simplest, so the bitmap in memory, but you know, you could have bitmaps in lots of different sorts of applications. But now the shape that we've defined doesn't care about which of these implementations as long as it has setPixel and getPixel available as methods. So the shape is in some sense detached from all the complex concrete domain of how the bitmap is stored in memory or on a server or in the GPU, etc. It's just a shape. This is a form of abstraction, of separation of concerns, and loose coupling, because it's very important that the details of one implementation, the shape in our case, don't interact with the details of another implementation, the bitmap in our case, so that we have less possible interactions between these two domains as the least possible number of interactions, because, well, then the domains will be easier to think about, and brain power and attention and short-term memory are the resources that we as developers have to be very mindful about. Let's move to an implementation. Let's define an array bitmap. Okay, so the array bitmap will clearly implement bitmap. Now this is an older style of working with types and programming, so you might recognize that this is not as seamless as the structural type system of Typescript, which just automatically recognizes that something has the right shape and just allows to put it there. Here we're stating that the array bitmap will conform to the shape of bitmap by name. So this is the nominal doctrine of type systems, because we connect array bitmap explicitly to the bitmap, not implicitly by a matching structure. I'm also going to do something pretty ugly. I'm going to define the width and the height as constants. Okay, as you can imagine, in a real implementation there would be a lot more. Notice that the compiler is complaining because it's saying that array bitmap does not correctly implement the interface bitmap because it's missing stuff. It's missing setPixel and getPixel. One interesting advantage that the IDE makes explicit is that when we tell Typescript, hey, array bitmap is supposed to be a valid implementation of bitmap, well, then we do get a handy button that says implement interface bitmap, which saves us from a bit of copying and saves us from some potential errors. So, you know, not bad. Okay, let's also define a constructor. Let's define the pixels array of arrays, so by row. So for First the rows, then the columns. Obviously, the thing now is complaining because pixels is not initialized, it's not definitely initialized. Okay, now just out of laziness, let's import the range from immutable library. Okay, we have seen it already. Okay, so for each row, what do we do with a row? Well, nothing, because this is just a number, so the underscore we ignore, that's the index of the row, but what we do is now we return for each row a column. And what's in the column? Well, also here this is the column index, the second iteration variable, but we don't care about this. What we do care, on the other hand, is that we want to create a pixel with all black, so as pixel. Okay, but this doesn't work yet, because the type that we're trying to assign is a sequence of a sequence containing a sequence of colors. So now we have to perform a series of transformations to array. So now this is a sequence of arrays of pixels, that's good. And finally we make an array of arrays of pixels. Okay, just please allow yourselves to find this complicated. If it's the first time you see such a composite query, it's okay. I've been doing this for 23 years now, so yeah, I'm kind of cheating. I sort of know this pattern by heart, so you know, take your time to appreciate something like this. Okay, anyway, so now we have an array of arrays of pixels which are set to 0, 0, 0, which is the same as black. Very simply, when setting a pixel, what are we going to do? We're going to say pixels of, well, we go by row, then by column, and then, well, we simply put the value of the pixel that was passed to us inside this cell. And to get a pixel, there we go. Again, simplest implementation possible, could be a lot more complicated. Now is where things become interesting. Let's define an interface. An implementation of shape, for example, a square that implements shape. Again, we get the IDE suggesting to implement the interface shape. A little bit of help. Every bit of help counts. Okay, so for each row, and we have a fixed height, then for each column, and we have a fixed width. Okay. Well, in this case, we want to set a pixel on the target, but to what column? To what row? To what column? But what color do we want to set? Well, we might make the implementation of square a tiny little bit more sophisticated. Let's accept the color as a pixel. We assign this color field to the color parameter, and here we can put this dot color. Okay, so we have squares of potentially different colors. Again, this implementation should be more sophisticated. The square should have a position starting from a minimum, ending at a maximum. So there should be a lot more. Oh, by the way, this is a rectangle in case the width and the height are not the same. So once again, there's plenty of things that should be made more sophisticated were this an actual application, but it isn't, so we are fine. Now I'm also going to be very lazy and just copy this to define the implementation of a triangle, which will also take a color as input, and then for each row, and then for the columns up to the current row, there you go, we just set the target pixel. So this is going to cover each rows, but then the columns up to the row. So it's going to be, I think the bottom left quadrant, I guess, yes, but we will see it in a moment. Okay, cool. Let's also add another method to the bitmap, because we want to be able to see the bitmap. So we define toString. toString is one of those special methods that implicitly get called when, for example, using a variable or an expression within string interpolation. So toString is called automatically, and if we don't provide an implementation of toString, a sort of standard implementation will be provided for us. And in toString, what do we return? Well, okay, let's take all the pixels. I know what, I'll do this. I'll do this a little bit more explicitly. Okay, so we have the result. Then we have to go through the rows and the columns after having put a whole row. Obviously we need to have /n. And how do we deal with the single pixels? Now this is printing on a console, so we have to do this in sort of grayscale. What we're going to do is we're going to use the space for colors that are too dark, just a slash for colors that are somewhere in between, and an X for colors that are very light. So we get the average of the pixel. So const RGB is equal to this dot pixels of row and column. Because this value here on the right side, we know it's a tuple of 3 elements, then it's safe to simply perform a so-called decomposition of the tuple right away. So these two things, the thing on the left and the thing on the right, they match already. So well, TypeScript allows us to do this. It's very, very clean. Then we can take the average, being R plus G plus B divided by 3. Now, we're going to make the executive decision that our color components RG and B are floating point numbers, so they go between 0, fully off that component, to 1, fully on. So our range is 0 to 1. Now, the result will be, if the average is smaller or equal than, say, 0.3, then, well, we put a space. Otherwise, if the average is smaller or equal than 0.65, we put the slash, and otherwise we put the full color. Very, very, very ugly, but yeah, also in its own way refreshingly simple. Okay, good. Now, we can define our bitmap. Okay, now we have the bitmap. Notice though that here bitmap obviously has type array bitmap, but I could even say that bitmap has type just bitmap, and TypeScript wouldn't complain. Why? Because array bitmap can be passed wherever a bitmap is expected. We can pass an array bitmap to a function expecting a bitmap. We can put an array bitmap in an array of bitmaps. This way we forget about the specific details of the array bitmap, in case we don't care about them, which in most cases dealing with bitmaps would be true. And we only remember at the type system level, of course, because at runtime an array bitmap will always be an array bitmap, but at the type system level we forget about the unnecessary details of anything else but the fact that a given variable is a bitmap. We do the same for the shapes. We declare an array of shape, and obviously, well, a shape is an interface, and an interface cannot be instantiated because it's an incomplete thing, so you can't say, hey, I want to have a new shape. No, it doesn't matter. You can have a triangle, you can have a square, and this is exactly what we're going to do. We're going to pass a square, and the square will be white, and we are going to pass a triangle, and the triangle will be just let's say okay, it's going to be red and blue. Okay. Oh, pardon. Yes, this of course has to be passed as a pixel. Very good. Notice that even though the array is an array of square and triangle, I'm just saying, no, I don't care about the specifics of the types. It's just an array of shape. In case I were to remove the type, then TypeScript would infer this to be an array of square or triangle, which is perhaps too specific. I just want an array of shapes, and if later on I want to be able to add anything else that is a shape, then the type definition here, the type declaration is very important because it makes it possible to also put later, in shapes with push anything that is a shape. So if we had 50 implementations of the shape interface, then it would be possible to add any of them by calling the push method. But if we let TypeScript incorrectly infer that shapes will only contain squares and triangles, if we had something else that is not a square and triangle, we wouldn't be able to add it. So this is interesting because it's really forcing TypeScript to accept, okay, I don't care about the specifics, I just want the generic thing, as long as it's a shape. So this is, again, quite powerful. Now, we can go through all the shapes, and for each shape, we can draw it on our bitmap. And finally, we can print the bitmap. We can print the bitmap, having some trouble typing here, and I will use string interpolation in order to force the invocation of the method to string. Okay. Well, there's just an X, so that's clearly not what we want. Let's take a look at what is happening here. Oh, well, of course, this only keeps the last pixel, so how about we add to the result each pixel. Okay. Alright, something is going wrong, but that's life. No panic. Let's just see what happens. First of all, let's remove everything and let's see what happens. Okay, it's empty. Now let's remove the square, because clearly the square is doing something that we're not expecting. Okay, all the pixels in the triangle are being seen as white, so the program is probably working, but the threshold 0.6 65 is perhaps too low. So let's say that we put white when all the components average to 85%. Okay, now we get the slashes, and let's restore the square. 1, 1, 1. So this is certainly white, and there you go. Now you have the white background on top of which the triangle has been drawn. Okay. You could imagine that in a more sophisticated implementation you could have filters on top of shapes. So you could have okay, I'm going to just sketch the implementation, because we should have more sophistication in order to even be able to implement this. But you could have, for example, a flipped shape which implements shape. And well, the flipped shape, what would it do? It would take as input a shape, and in the constructor obviously save the shape. Pardon, this would actually have to be a shape. It would save the shape, this dot shape is equal to shape, and then when drawing, what would it do? Well, it would draw on the target, but it would use the shape and, for example, turn the X and the Y around. And interestingly, you could then say, okay, I want to flip the triangles. I could say, okay, flip the triangle, and because flipped shape is a shape, well, obviously, okay, there's an error here, so let's just implement it with the placeholder. Okay, now you can see, okay, the flipped shape on top of a triangle also fits the array of shapes. And we really don't want TypeScript to guess, oh, this is an array of squares or flipped shapes. This would be very silly, because well, why do I even care? So interfaces also allow all of these beautiful patterns where you say, okay, this is a shape, but a shape doesn't need to be implemented as a basic shape that directly sets the pixels. It can also be a transformation. This is a design pattern that is encountered quite often in real life and in practice, where you take an instance of the interface and you put some extra logic, which I'm not doing today, on top of it in order to perform some transformation. This is often called the decorator pattern, because you decorate an implementation of shape, being the parameter you get, with some extra logic. So you could have things with borders, with shadow, etc. Those would all be implementable in the form of decorators. Now, so the power of interfaces, as we've seen now, is that, first of all, they let us forget about the details of a domain. By virtue of having the bitmap as an interface, we have been able to effectively forget about the implementation of bitmap while we focus on our implementation of shape. This introduces just a barrier between one group of classes, which you could then move to another file, even to another project, to another package. It doesn't matter, you move it away, out of sight, out of heart, and especially out of short-term memory, because as developers, again, we can't really focus on everything at the same time. It doesn't matter how incredibly intelligent and talented a developer is, eventually, if they don't start splitting things, they will run out of memory, of short-term memory. They will be unable to remember all these details at the same time. So we take the bitmap and we don't think about it anymore. We would move it into another file to facilitate this not thinking about. It's really what we do, because for the compiler, for TypeScript, it doesn't really matter. You could have everything in just one big file and it would just be, well, super happy. But all this splitting, it's really meant for us. It's a way for us humans to organize knowledge into little clusters, and the interactions between clusters are very often interfaces. You might have also noticed that interfaces are, in a sense, look a bit different and a bit less seamless than the normal type system of TypeScript. And that is true, because interfaces and object orientation, classes, etc. are a bit of an older concept, and TypeScript has very wisely decided to just connect to the tradition of how most developers are used to doing these things, rather than trying to figure it out again. So that's also why you might notice that with respect to the structural type system, this whole constructor thing, it feels a little bit unwieldy, that is true, but it also has to do with the tradition of object orientation, and there's nothing wrong with that. Now, something that object orientation has introduced a long time ago is the concept of a type extending another type. You will notice that this kind of functionality of the type system does overlap with the type algebra of the operators and especially, well, actually both and or in slightly different ways. Let's dive into it. Now, let's say that we have a new interface which defines, well, actually, you know what, let me still keep the interfaces bitmap and shape, but let's say that we want to add a width and a height. Okay, and we want to state that the bitmap must have a width, which is a number, which I'm marking as read-only, and also a height. It's quite healthy, actually. It's better than the previous implementation, because as we stated, well, the width and the height shouldn't just be, you know, constants. But the shape also has a width and a height. There is a doctrine in software engineering that states that repetition of code is dangerous. And also, out of personal experience, as well as common sense, I can wholeheartedly agree this is true. It's a good thing to avoid repetition of code. Why? Because, well, right now, we're introducing an implicit standard across two related domains, the domain of bitmaps and the domain of shapes. And the standards are, well, that in the bitmap world we have the width and the height, small letter, numbers, and in the domain of shapes, small letters, numbers. Someone might later on decide, okay, for whatever reason I want to do this Java style, so get width and get height. And there is nothing that's enforcing consistency between the two domains of bitmap and the shape. And this is bad, because lack of consistency increases the strain on your brain as a developer. And as we covered already, this is the most scarce resource, short-term memory and focus. So we want to reduce the cognitive effort as much as possible. Okay, great. So we want to find a way to keep these two things connected, because they are expressing the same concept. What I'm going to do is I'm going to define a new interface. Let's call it sized. surface, perhaps, whatever. This interface has the width and height, and then I'm going to say that the bitmap and the shape both, extend the surface. This way, if we want to add something to the surface, for example, make the width and height not read-only for whatever reason, that's great. You know, this change is immediately reflected in both the bitmap and the shape. An interesting side effect of this is that if something expects a surface, we can pass a shape to it. Just like it was possible to pass a square wherever a shape is expected, now we can pass a shape or a bitmap wherever a surface is expected. I don't want to implement everything to just show this feature of the language, so let's say that we have a function f that expects a surface. Actually, at least let's give this a better name. Process surface. Okay, and here we have all of our code that, well, has not much to do with the surface because it only has a width and height, but you know, bear with me. Then let's have a function f takes as input a bitmap. Okay, what f may do is call process surface and passing the bitmap to it as an argument. Why? Because the bitmap has strictly more things than a surface. So if something like process surface expects a surface and we pass it a bitmap, well, okay, we're also passing more stuff, in our case set pixel and get pixel, but having more stuff that is just there, you know, latent and sleeping and not really doing anything, it can't really cause any damage. And process surface may not access set pixel and get pixel unless we use some moderately weird and slightly unsafe cast to bitmap with the as operator, but this is unsafe because we have no guarantee here that process surface is being invoked on a bitmap. So this is, yeah, this is called unsafe, and even though the term sounds a bit dramatic, it actually is unsafe, because if we define another function g that takes as input a shape, and now we call process surface with shape, well, obviously, again, the compiler is not complaining. Why? Because the shape contains also the draw method, which process surface may not access. It's just for the purposes of a process surface, it's just extra ballast. In general, what you will see is that first you call a function like process surface that takes care of something generic that is only related to shape and bitmap being surfaces, and then you can do whatever else that is only specific to shape actually being a shape. So you have these sort of drill downs, because if you think about it, when we call process surface, we're sort of doing a drill down into the domain of surfaces, doing whatever we want to do with shape or bitmap as a surface, which apparently is some shared common logic that we managed to factor out. And then after this, we bubble back up. I just like the concept of narrowing, because we narrow into the domain of surfaces, and then we widen back up into the domain, in this case, of bitmaps. So here, narrow down to surface, and here widen back up to bitmap, and here, well, we are widened by default to bitmap because we have bitmap, so it looks sort of like an inverted cone, you know, a traffic cone, or you start at the bitmap, you dive down into the funnel, then you come back up into the bitmap, and the domain widens again. And the same happens to process surface. I do like to try to visualize these very abstract things. Now, something that's also possible, and let me now use an abstract example now. No, not an abstract example. Let's actually keep it concrete. We can also use extends for classes. Let's say we have an animal class, and we only have a move method. Okay, and now, okay, console.log, moving. Okay, so this is what move does. Okay, and all animals in our domain, whenever we call the move method, well, they just print moving. Very exciting application. Okay, now a dog is an animal, so dog extends animal, but, well, not all animals woof. So well, I have a duck in front of my house, and she just had ducklings, so I can absolutely tell you, day in and day out, night in, night out, she clearly doesn't woof, but she quacks. Okay, but the dog does woof. So we can't say that woof is a method of animal, but we can definitely say that woof is a method of dog. And console.log. Woof. Okay, very good. A duck, on the other hand, well, extends the animal because both animals can move, but she also quacks. Okay, I can attest in this very specific period of my life. So, quack, 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 quack. Okay, so this particular duck is like the one in front of my house, quacks a lot. Okay, now, and you know, you can define as many animals as you want. Now, let's say that we have a bunch of animals. Okay, and we state that animals are an array of animal. Okay, now I can put a dog here, I can put a duck, and if I want to go through all the animals, the only thing I can do is I can call move. I can call move because, well, that's the only thing we know. So in that for each animal, in our case, will be either a duck or a dog. And so we can't really know when to call woof and when to call quack. So the type checker makes sure that we keep it safe and limits us to only do the things that are safe. If I, on the other hand, were to create the dog like this and actually keep track of the dog, well, no, that's okay. Now here we also have an example of, here we're in the wider domain, here we've narrowed the dog down to animals. Now we make all the animals move, but then we can widen back up and say, okay, dog can also move. Okay, huh. So if you want to be able to widen back up, you must keep track of the thing that you are going to narrow down. Which might make sense, because here you might move this to a separate function or whatever, have some principles of, you know, some much more complex processing than just a for each. So this thing works. This thing is an actual pattern, this narrowing down and then widening back up. And now duck may also be led to quack. One word of warning is that if you don't specify the type of animals, then Typescript is going to infer that this is an array of either dog or duck, which limits our ability to then say we also had cat. Okay, cat, meow, meow. Okay, very good. Now, if animals has been inferred as being either a dog or duck, then if we want to add with push a cat, it is not allowed, because animals has been inferred as overly restrictive. It's actually quite important to give the hint either by casting, and this is a safe cast because obviously every dog and every duck is also an animal. Either we cast a dog and duck down up as animals, and then animals is correctly inferred as an animal array. This I don't like. This feels a bit too much. Or we say that this is an array of animal, and then I might also want to type it correctly, and then animals.push new cat works because, well, cat is also an animal, and so the subtyping does its job in correctly saying, okay, you want to forget about the specifics of the cat, so you want to forget that the cat can meow because you only care about the fact that it can move. Okay, sure, good for you. It's also possible to say a known type here, or any. You might see these things sometimes. Be aware that this is sacrificing type safety completely, and so here animal doesn't give any suggestion. So be very careful and do not underestimate how much grief the choice of saying, oh, okay, let's just put any, the compiler is going to stop complaining. Because if the compiler is complaining, there's a reason for it. So, you know, embrace the compiler complaining. That's That's good, you know. Just like we can put a dog and a duck into an array of animal if we have a function, let's say move animal, that takes as input an animal, and then we call animal.move. So we do it twice, move animal twice, yes, okay. Now we can call move animal twice with a dog, we can call it with a duck, and obviously we can also call it with a cat. Once again, this is subtyping polymorphism, which is very similar to the structural to the structural type system that allows, you know, these automatic conversions, but in this case the conversions are a lot more explicit. If you were to say that meow is in animal though, oh, pardon, something interesting now happens, because now Typescript has guessed that animal has a meow method, but in our case it can't really guess that animal happens to be a cat. There's a very neat trick actually that I would really like to show, which is the so-called visitor pattern. This stems from the design patterns doctrine that was very old. So let's say that we know when defining the animal that the animal is going to be either dog, cat, or duck. Now, we do have discriminated unions nowadays in TypeScript, so those are actually a much cleaner way of doing this, but, you know, let's do this anyway. Okay, so let's add a visit method, and okay, so what's the visit method going to do? The visit method, because remember I stated that we know that an animal is only going to be either a dog, a cat, or a duck, and nothing else. So it's a closed set of variables. So we're limiting polymorphism. We're making a strong assumption. Okay, so now let me redefine the type function that we had already. Actually, input and output, yes, so this is just input into output, because I really don't like to type this open bracket, colon, close bracket, equal, greater than. It just kills my fingers. Maybe you're better at this than I am, but I suck at this. Okay, so now visit is going to take three parameters, which are lambdas. One, because it's an animal, but we don't know which one of the three options it is, so we're going to accept what to do for each option. So what to do if I am a dog, and this is going to be a function that takes as input, well, it takes as input a dog, and just returns void for now. We're actually going to clean this up. And then what to do if I am a cat, takes as input the cat, and what to do if I am a duck, which takes as input a function from duck into void. Okay. Now visit is void. Problem is that, well, when working with the animal, it does suck a bit because I don't know yet which one of these three functions to call. So I'm going to mark visit as abstract, and I'm also going to mark class animal as abstract. Now notice that I do need to provide a return type. For now I will put void. Because, well, which of these methods to call, of these lambdas to call, is only known to the concrete implementing classes. Now, implement all inherited abstract classes. Okay, and notice that now we have the visit method. And look, because I clicked on all, then TypeScript magically did it for cat and duck as well. Okay, so now, in this case, we're inside the dog. So here we actually have this, and this has type dog, so now I can simply call what to do, oh no, what to do if I am a dog, and call it with this. And look, it's happy. And what if I accidentally try to call it with what to do if I am a cat with this? No, it doesn't work, because this has type dog, and what to do if I am a cat only works with cats. Okay, so what to do if I am a dog, what to do if I am a cat, and I can pass this again because this here inside cat was a cat, and what to do if I am a duck with this. Alright, abstract classes bridge the gap between classes with an implementation and interfaces where the methods do not have an implementation. Whereas before I could have, before animal was abstract, actually said new animal and it would have worked. Now I cannot. Now I cannot say new animal, which actually is a better behavior. And why can't I say new animal? Well, because it says you can't create an instance of an abstract class, which makes sense because the visit method does not exist. So suppose that I want, after moving the animal, simply show a diagnostic message that says, okay, if you're a dog, I want to just say, okay, we move the dog, otherwise we move the cat, otherwise we moved the duck. So here I provide the lambdas, and well, this is the dog. I could, well, make it woof or whatever, but I don't really care, so I'm going to ignore the parameter, but it's nice to have it, because this is the dog that just that we just made move. So we moved the dog. And in the case of cat, and this is sort of like a switch statement, you know, or an if then else in a sense. Here we do console.log. We move the cat, and finally, in case of the duck, oh, I really dislike this misalignment. We moved the duck. There you go. And okay, we're ignoring the parameter, but in real life, when exhibiting a visitor, you are probably going to make use of this parameter. Let's do it actually. So let's say that here we have the name. Okay, let's say there's a name, read-only name. Oh, now we need a construct. Okay, we would need a constructor. I'm not going to fix it completely, but what I'm going to do, I'm going to show that, for example, here we could say we move the dog name, and here we could do we move the cat, and then also here cat.name and so on. So, well, provided that that we had fully implemented this this name property and this initialization in the constructor. All right. Now, first of all, I'm going to make a slight change, because more common names for methods for lambdas such as these would be onDog, which also really makes sense. Well, on as in in case of a dog, you know. onCat. You might recognize this because many event handlers have names like onClick, onLoad, etc. So this is a little bit a similar principle to event handlers, but the events are, well, the discovery of how the class was initialized. The fact that we can't really extract any information from the visitor method, though, might cause us some challenges or some troubles, because right now, okay, visit can only get a void parameter, a void value back, which is not really a value because it doesn't contain any information. But it is possible to extend visit in order to become generic. If we make it generic, because any instance, any method, any class, any interface can be generic, like this. Well, this wouldn't make a lot of sense because something needs to be a container, so let's start with making the method generic. I could say that visit also has a type parameter, which is the returned information. And now, every one of these methods is supposed to give us the same returned information. I'm mildly surprised at the fact that, and obviously here the whole method will give back the same return information. The idea of visit now is that visit is generic, and as long as we provide 3 lambdas that know how to convert a dog, a cat, or a duck into this returned information, which might be whatever we want. Can be a number, can be another data structure, can be another animal. We might have something that converts dogs into cats, cats into ducks, ducks into dogs. Oh, let's do this. This is going to be fun. Well, that's a conversion to return information. And well, as long as onDog, onCat, onDuck can convert their type, concrete type of choice into the same type return information, then visit will always be able to convert an animal into return information. Now, the definition here is obviously broken, and as a matter of fact, the implementation is super simple, because now onDog, instead of being void, gives us return information. Now in this case, onDog knows how to turn a dog into return information. onCat knows how to turn a cat into return information, and onDuck knows how to turn a duck into return information. But here we can only call onDog, which does give us back the return information we wanted anyway, so we just return whatever onDog gave us back. Visit here, for the cat, well, the only thing it has to do is it calls onCat, which turns the current instance, this of the cat, into return information. And finally, visit onDuck, calls onDuck to convert this, which is a duck, into return information. Now, well, quite silly, but I could say that const shifted animal will be animal.visit of okay, well, if I don't put anything and I leave it like this, then shifted animal will just be, well, just be void, because console.log always returns void, and in this case the type inference works. But here I will say that visit will return an animal. Now I get compiler errors. Well, we start with dog, and now we're going to give a new cat back. Here, in case of cat, we're going to give a new duck back. So we're shifting the animals by by one. A bit nonsensical, but also cute. And now shifted animal has type animal. If we don't put the type here, what's going to happen? Well, now we get a compiler error, because a return information here was inferred to be cat, and now here we expect it to also return a cat. So in this case, the generic argument needs to be provided to the visit method. Otherwise, well, it's going to be very tough for TypeScript to guess what the proper type is. All right. Now, just to go quickly through this, every single instance, every single name in the world of object orientation and types can be marked as generic. So when we declare it, obviously. So dog could be marked as generic. Obviously now we get nonsensical compiler errors, because again, dog is also not really a type. Every method can be marked as generic. Well, woof now is generic for whatever reason. We don't even do anything with this generic parameter here. In general, also, if we have an interface, let's call it I, great imagination, we can also mark this as generic and then use the generic parameter, use generic, and then I take, I don't know, oh, pardon. Yes, then we can take as input an instance of the generic parameter, return the generic parameter, do whatever we want with it. One very neat feature of TypeScript that is also quite unique to the language is the ability to capture the concept of a constructor as a lambda that we can pass as a parameter to anything else. Let me show you how this works. So let's say we have a function, and let's say create and move, and this function will instantiate an animal and invoke the move method. Now, here we could say, okay, create animal, and we could say this is a function that takes as input nothing, whatever, void, and returns an animal. This would be essentially equivalent to a constructor. Then we could say animal is create animal. We don't really pass an oh wait, how silly. Let's say that I pass undefined. Yes, very good. Then undefined, and then because my fun definition needs a parameter, but the animal doesn't need a parameter, then I call move, and that's it. Okay, so this would be a way of doing this, and then I could call create and move. wait, what did I include? Domain. No, that's not what we wanted to do. Create and move. And I have to pass a create animal function, okay, and I could say I ignore the undefined value, and then I return, for example, dog, okay? Now this could work. A very neat, and in my opinion also quite elegant feature, allows us to skip this translation step, which is perhaps quite unnecessary, and say, okay, create animal is a function that corresponds to the new operator, so the constructor takes no parameters and returns an animal. Here I can call it as if it were a constructor. Even better, I can give it a name that simulates or resembles the name of a constructor. How do we invoke it? Very cleanly, because the name of the constructor is the name of the class itself. When you call it, you can just pass the name of a class, and you might notice, okay, but wait a second, here you specify animal, but here you're passing dog, and I might even pass duck or cat. Why? Because the constructor of cat, the constructor of dog, and the constructor of duck, they all return, well, obviously a cat, a dog, a duck, but because of subtyping, because of inheritance, well, they also return an animal. So there you go, that's why it works. So here we're stating that create and move expects a constructor that returns an animal, and here we're passing a constructor that returns a cat, which is an animal, therefore a constructor that returns an animal. Very elegant. Now suppose that the dog had a name, so read only name, which is a string. Let me see if the IntelliSense. No, this I don't like. I was kind of hoping, like in C# that you could add it to the constructor. That would have been very cool. Like you add this initialization to the constructor. And what am I missing here? Oh, okay. Okay, now this is also interesting what we're getting, because we got a complaint saying, okay, the constructor for a derived class, because this is a derived class because it extends something, must contain a super call. Super refers to the constructor, super in general refers to the inherited class. So super is animal in our case. Let's see if we can do anything with it. Yes, look, a super is like this, but it refers to the inherited class. So super really is the same as this, but with type animal. So you have this, that's, you know, it has a move, name, visit, and move. And you have super, and super only has move, because that's the animal. Okay, quite exciting actually. Now, and by calling super with brackets, yeah, this is one of those things you just need to know. And I think this one is a little bit ugly, but we'll see in a moment that perhaps it also makes sense. Well, we explicitly invoke the constructor of animal. So this is calling the constructor of animal. If we decided, and this is going to be a little bit annoying because, well, now we have to fix it in 3 places, but that's okay, that there's a name in animal, well, then the name has to be initialized in the constructor of animal. So let me copy this. Again, a little bit of laziness. Now, there's no super here. So this initializes the constructor of animal. And here, well, in the call to super, we actually get a complaint saying that, well, super is expecting an argument because now the constructor of animal wants the name. And actually, let's fix this for the cat and for the duck. And there you go. Now look, here we get a compiler error because it says, okay, the animal, here we're passing a constructor that doesn't take a string. Pardon, that takes a string, whereas what we declared here is that this constructor takes nothing and gives us an animal back. Okay, so here we have 2 options. Either we... okay, no, we don't really have 2 options. We have to adjust this. We have to say that this constructor takes as input the name, and the name will be fluffy in every situation, and now all of a sudden create a move when passing it cat, works correctly because now the constructor that create a move is expecting takes as input a string and returns an animal, and that's exactly what the constructor cat does. It takes as input a string and gives back an animal. Now, let's also adjust the woof method. Let's say that we want to state who is woofing. So one could say this dot name says woof. Okay, very good. Now notice that we can access the name through this, because of inheritance, of course, because dog extends animal, so anything that's in animal is also in dog. But we might also access the name via super. I don't think this makes any conceivable difference, but yeah, it's interesting to see that Typescript is correctly reporting that in super we only have name and move, and in dog we have in this we also have the rest. It's also funny, you might notice that in animal there's name and move, but there's no visit. So let me show this again. The super we have move and we have name, but if you want visit, you have to be in this. It's interesting. So super is not exactly this cast to animal, because if you were to say this as animal, which is safe to do because obviously this extends animal, then here you would have visit. So super is like the concrete instance of animal. So it's a little bit less than just the animal. Okay, now here in create a move we are getting the constructor of an animal, and there's yet another little trick that I would like to show you. Namely, we could make this generic, and in the actual animal, and we could say, okay, as long as the actual animal extends animal. This is an example of a generic constraint. So here, create a move accepts any generic argument that inherits from animal, that extends from animal. And here we can say that the constructor that we provide must return this actual animal. Now, what happens here is now different, because when I say create a move cat, I'm not performing any cast, any conversion from cat to animal. So I'm not saying, okay, this is a constructor that gives an animal back. I'm saying this is a constructor that gives a cat back. And the only constraint is that whatever type I pass here, which also automatically becomes the generic argument, needs to extend animal. Let's say I have something else, like a tree, okay? And let's say that the tree also has a constructor that takes as input a name. If I were to try to pass tree here, it wouldn't work. Because, well, it says the type of tree is not as, oh yeah, okay, let's look at it in the console. The type of tree is not assignable to parameter of type new name, string, animal. The type of construct signatures are incompatible, blah blah blah. Okay, so it makes sense. It's basically saying that a tree is not an animal. And if I were to put it here, though, then I get a slightly different error, because now I get the error earlier. It says, no, the type tree does not satisfy the constraint. This is the constraint. Does not satisfy the constraint animal. Ha. It's also saying that it's missing properties, so the structural type system might also close an eye if will close an eye if tree can be converted and has the right fields with the right types. So it doesn't need to exactly extend from animal. So by doing this, especially if we wanted to say, okay, return whatever it is that you want to return, that you created, return the actual animal, and here we say return A. The difference now is actually quite significant, because if I go back to the cat, oops, const C is this, the type of C now is cat. So remember when we discussed the narrow down and widen back up, well, we're not losing information about the fact that whatever create and move has created and moved is also a cat. If we were to go back to the previous version and we wanted to return whatever was created by this constructor, then here only thing I could do is return an animal, And now the type of C, even though we know we created a cat, it's animal. So here, the fact that we want to pass the constructor and perform some operations inside create a move forces us to stay narrowed down in our specification, which is sometimes less than ideal. Whereas this has the right combination that inside create a move. Okay, we just treat A as an animal and, well, don't look further into what is it specifically, because we just need to move it. But by returning it and returning it as an actual animal, so the generic argument that was passed to us, when we bubble out of the create a move function, well, whatever comes out of it has the precise type that we initialize the variable with. So quite powerful. We're going to dive a lot deeper into generics and the way they work later when we discuss advanced TypeScript, but that's another course. We're going to have plenty of fun there. Now, let's move on. We're now going to talk about properties and static versus instance fields, and well, then close this very long and challenging lesson. Alright, now, properties are some special methods that behave like reading or writing a field. Let's create a very simple class. Let's not even bother with giving it a proper name. Let's call it C. And let's say that C has a private field. Let's call it length. What does private mean? Private means that no one can change or even read the field length besides an instance of C. So this also means that not even someone who inherits from C can see length. Let me show you. Let C is new C. We don't get to see length. If I were to mark length as public, which is the default modifier, now all of a sudden I can do whatever I want with length. This is very useful in order to perform what we call information hiding or encapsulation. So we want C to behave like a unit. C has its own logic for updating and managing the length, and we don't want anyone else outside of C to mess with this logic, because if you were to just tell everyone in your team of developers, if you work in a team, or even try to tell yourself in the future, hey, remember, don't mess with the length, because it is an internal field with its own logic, and if you mess with it, you break everything else, the chance that someone or yourself in the future is going to forget about this is, well, not a chance, it's an absolute certainty, it's 100%. Also, if we were to have a derived class that extends from C, you might have noticed that I type the colon very often. It's because I've been doing C# programming for C and C# programming for a very long time, and in the languages of that family, inheritance, so implements and extends are a colon, so that's why you see it all the time. It's not like I'm crazy or whatever, or I have a special key that gets in the way. That's the reason why this is happening all the time. So let's say that we were to set up a new instance of D. Well, D obviously doesn't have the length, but also here, let's say I had a method M, and I try to call the length. I don't have it because length has been declared as private. If I were to declare the length as protected, on the other hand, there's the length. But outside of the class, there's only method M. So what does protected mean? Protected means, okay, I accept that anyone who extends me will be able to access this, but outside, let's treat it as if it were private. So protected is, because usually the inheritance hierarchy, so anyone that extends a class, we can consider them to be basically just an extension to the class itself, and so allow them to see private stuff. And private is a very, very, very restrictive modifier. So you might encounter, especially in heavily object-oriented code bases, more protected fields than private fields. Private is like super brutal. No one can touch or see this but myself. So that's super defensive. That's a little bit uncommon. It's too defensive. Okay. So we have private, we have protected, we have public. And one of the very interesting patterns that arise that we can give body thanks to private fields are properties. So with a property, we can say, okay, whenever someone tries to read the length, not with the underscore is one of the many conventions that are commonly used in order to signal that a field is private, so that no one can see it. But so we could say, okay, when someone tries to get the length, notice that I'm using a new syntax, and the light blue of the keyword highlighting is making it its appearance. Whenever someone tries to read the length without underscore, then we return the length, the underscore length, this dot underscore length. Let's take a look at what happens. I instantiate a new C. Now I don't have the underscore length, but it can read the length. Oh, pardon. The beauty of this is that for whoever is using class C and reading the length, this looks like a normal field being read. But in practice, a method is being invoked. This length method, it's being invoked. We can do stuff when invoking this method. I could say, well, for debugging purposes, the length is being read. Okay, there you go. Now when I run this application, we print 0, but we also get the length is being read. Adding console.log to whenever we read a property is not really the best. So the length is now what we call a property. It's a fake field. It's a computed field, or whatever you want. Things become particularly interesting when we want to control how the property is assigned. Now, when trying to assign a value, oh, look what's happening also. It's guessing that the value is a number. We can also declare it explicitly. And this dot underscore length is equal to the value. Now we assign it. And here we might want to debug stuff. Or we could say old value was, and then this dot length, new value is value. I have to say, this bit I recognize having done it a few times in life. Can we do c.length plus plus? Yes, we can. Now this is just translated as an assignment. And what do we see? We see old value was 0, new value is 1. Let's do this many times. 0 to 10. And see. The IntelliSense really wants to use the name of the class for this. Okay, and then you see old value was 0, new value is 1, old value is 1, new value is 2, etc. Now, you might imagine how incredibly powerful it can be to be able to define fields that are as comfortable, as handy, as easy to use as regular fields, also syntactically without having to call methods, while at the same time being able to customize the code around, before or after, the changing or the reading of the field. In our case, what we just did was to add some very simple console logging. But one might also say, okay, the information in this field is so insanely important that I want to save it on the hard disk. So I could have include the file system package and say, okay, right after this, right after saving the value, I could write. Oops, yeah, I don't have the bindings for this. Backup.json, very annoying when you get to the point that you are rightfully, I think, reliant on IntelliSense. It feels like you're being cheated when the IntelliSense disappears. Okay, and this is it. Okay, now let's see what happens. Obviously, the program, okay, is not perceivably slower, but it has become a lot slower. And in bin we have the, no, not in bin, here we have the backup.json, where the length is 4. I am wondering why. Did I type it by accident? Oh yes, I did. Okay. And so we're backing up anytime we modify the length. We are writing to backup.json the last version of the file. This is very interesting because the user has no idea. The user as in the programmer using your class C, is just increasing the length, and they have no idea what's happening under the covers. But what you are doing is you are making sure that any change to the length is permanently serialized to the hard disk for backup purposes or whatever. And well, obviously, imagination is the only limit, but you could imagine, okay, there's logging information, but you could also perform API calls to synchronize data to an external service, perform some validation, like if there's a complex validation logic and someone tries to set the length, but you want to validate that the new length actually makes sense, is allowed, or whatever. Yeah, you can do so many things, and every one of those things will be neatly hidden from the user of a class, so that the client code doesn't really have to worry about the underlying validation or business logic, and thereby achieving a better separation of concerns. So yeah, properties are very pretty, and it's nice to also know that they were invented quite a long time ago. Well, they were made popular, they truly became mainstream with C#. C# introduced them, I don't know, somewhere between 10 and 20 years ago at this point, and they were very often described as really the neatest functionality of C# as a language when compared to Java, back at the time when C# and Java were competing for who's the prettiest language. There was a very major competition in the world between the two camps, C# and Java, and yet I'm happy to see that other languages like TypeScript are picking up properties and making them work well. We conclude the lesson on object orientation by talking about static versus instance fields and members. Okay, so we have seen that classes have instances, and every instance of a class carries its own state in the form of a fully independent block of memory where the data is stored for that separate instance. Sometimes it is useful for all instances of a class to share the same fields or methods. Now this is not super common. Usually when you use object orientation, you don't really want to make something globally available, but for logging purposes, for implementing a shared pool of resources, a shared counter, etc., it is actually handy to have some data which can be shared by all instances of the class. And these are the these shared members are called static. Let me show you. Let's say we have a class C, and we want to have a variable counter which is accessible everywhere. Static counter. Now, by marking the counter as static, I'm initializing to 0 right away, so I don't need to state that it's a number. Then the counter does not belong to a specific instance. Now, if you were to have a method, just an instance method, you wouldn't see the counter as part of this because it's not part of this. It is part of the global instance, so it's available everywhere. So if you press C dot, then you will see that among the various things that you can do on C itself, you also have the counter. Now, so this means that whenever we call the instance method m, we increase the counter by 1. We can also make a method part of the static family, so m is not an instance method anymore. What this means is that if I were to initialize a new instance of class C, and I would try to see what's in the what's available to us, well, there's nothing, because m is static and the counter is also static. If I want to access the counter, or I want to access m, here they are, accessible statically. I don't need any instance of the class itself. So here I can call m, I can print the counter, I can do whatever I want. So, and you might wonder, okay, but what's the difference between static fields, static methods, and the global fields and methods? Well, it's just a matter of scope. It's just a way to hide them inside the class, because if counter and m only make sense within the context of a given class, well, Might as well just put them in there rather than pollute the global scope where you don't really want to put anything, because the global scope is, as a matter of fact, should be empty, with the exception of those things that you need for the application that you're building. Now, obviously, visibility applies as well. So if we make, pardon, okay, so private has to be put before. Now you can see that M can access the counter because we're in the same class. So there we go. No one can touch it. I'm wondering whether we can put protected. I'm guessing yes, we can. Okay, and we'll play around with it a little bit. Outside the class, in the global scope, we can't access a c.counter anymore. So there you go. Static behaves reasonably with respect to inheritance as well. Let's say that we have a derived class D which extends C. Let's define an extend method N. Okay, now what can we do here? There's this. You might wonder what's the type of this. That's type of D, because in a static method this refers, so it's instead of writing C we could write this here and that would be the same. So that is the class we're working on. So we have counter, we have M, we have N, that's inheritance. I'm wondering if we have super. Haha, yes, we have. Now we only have counter and M, whereas with this we have counter M and N, the current method we're defining. And here obviously we have access to the counter because the counter has been defined as protected. If we turn the counter to private, then inside D we have M, we have N, but we don't have the counter anymore. Yeah, quite simple as a matter of fact. And also outside the class itself, if we check whatever is available to D, we have N, we have M, we don't have the counter again. Let's make the counter public once again, and now everything just works as expected, and we can access the counter through D, but also through C, and they are exactly the same counter. Now, one of the things I remember using static members the most was when indeed building a pool of resources. There was it was in the context of a video game where the recreation of entities was quite expensive because they had some GPU memory pre-allocated for textures and 3D models. So the idea was, okay, you have a big array of pre-allocated entities, and whenever an entity leaves the scene, leaves the screen, gets destroyed or gets deactivated, you just reclaim it in this static array, and whenever you need the next one, you just get it from the static array, and that's it. So the static array became a sort of memory pool or resource pool that made use more efficient. So that would look something like this. Okay, now this example is going to look really contrived, but let's say that we have the instance, the pooled data, and okay, this is just a number and a string. Okay, and here we have our pool, and the pool will be a list of pooled data. So import list from immutable. Yes, there we go. Okay, now in the construct. Oh, and here let's add the instance data. So this is just normal instance data, and we call it pooled data because it's pooled. Now in the constructor, say that we want to minimize the number of times we create pooled data whenever some pooled data is available. So what do? We check. Here, let's say that the pool starts with an empty list. Also good, yes. Or we might also pre-allocate some data. Why not? So we could say no. Let's pre-allocate some data. Say x is 0, s is empty string, and let's put 3 pre-allocated values. There you go. In the constructor, what do? We check if the pool. If the pool is empty, there's not much to do, then the instance data must be a new instance. Otherwise, the instance data can be initialized with pool dot again c dot pool dot pop. So I pop the last element. Oh no. Okay, there's one intermediate step. So top. So I okay, I'm having a last, and then c.pool.pop, and because lists in immutable are immutable, I have to reassign it. Okay, we might also want to capture this behavior here in a static method. Let's see if Typescript allows us. No. Okay, no problem. So let's just do it. Let's say that we don't really want anyone to mess around with the logic of the pool. We want to control it. Yeah, okay, that doesn't matter. Yeah, well, let's actually make it private, and let's make this protected. Yes, and protected will mean, okay, very good, that, okay, the logic for popping an element from the pool, all of this thing, will be captured by a method. So pop or create pooled data, and this will return yes. Now we have a little bit of separation of concerns. So here I can say, okay, in the constructor, I don't really want the class to mess around with its static logic. So I have sort of a separation of concerns. There's the static stuff and there's the non-static stuff. I might even put, we'll do it in a moment. Oh, yes, c.pop or create pool data. Yes, there we go. Why is it unhappy? Hey, no, it can't be. Oh, really? Well, this is not really true. Yeah, because Typescript can't really guarantee that last is there, even though it should know, because we checked whether or not it's empty. So let's simply force a cast. In general, forcing a cast is not a good idea, but well, in this case we have the proper guard, the proper check, so no issue will present itself. Okay. Now to finalize the strengthening of the separation of concerns, let's have the C pool. Okay. Well, this is all static, so I shouldn't have used the C, but I should have used this. Now you see why this is better than using the name of the class directly, at least for the refactoring purposes. Let's delete all these things. Now, pop or create pool data doesn't exist correctly, but if we extend from cpool, oh, okay, here we need a super call. A bit silly because the constructor of cpool doesn't do anything, so this might be added automatically. There are languages that actually do this, but that's life. Okay, and you see that I'm calling a c.pop or create pool data because through inheritance I can actually access all the static fields of cpool as if they were from C. Notice that C does not have the pool because we've made it private in order to create a little bit of protection. One might also want to add a release pooled data method that you have to call explicitly, that puts some pooled data back into the pool, and that you have to call when your business logic allows releasing that specific item. Now, I'm guessing this has been quite a tough class. There are lots of concepts. Object orientation is very difficult. This is perhaps the time also to remind my dear listeners, please be kind to yourself. Learning programming is very tough. It's a long journey. It's an incredibly fulfilling journey because, yeah, it sharpens the tools you use to understand and categorize reality. I do honestly believe learning how to program also makes you a smarter human being. It's like applied philosophy, a lot of philosophers in the previous centuries who try to describe the universe and its categories and structures, etc. And we do it on a daily basis, as programmers. But it's also very, very difficult, and there's a lot of logic and mathematics that's just hidden there. And, well, it doesn't matter if you see them explicitly, but there they are, and you have to deal with them. So be kind to yourself. Allow yourself the time to experiment, to make mistakes, to play around, and you will be excellent before you know it. See you in the next class.